Yay, now I'm recording. So we're going to work with PTK2 cells. So it's this one right here. It has some chromosomes and some microtubules in there. So if you double click on that, that is the one I'm going to use for the purpose of a distance transformation. So what we're going to do in this example is I would like to create a surface for the chromosomes, for the DNA. And I'm then going to create surfaces for the kinetochores and the dynectin. And I'm going to measure distances inside the boundary of my DNA as well as outside. So you can get a sense of how we can actually do that. So we're going to create a surface object for the DNA. So I'm going to label this DNA. And that's going to show me my little creation wizard in the bottom. I'm probably going to use the background subtraction option for thresholding because there are dimmer parts and brighter parts of the DNA. So to make it a little bit easier to see, I might turn off the other channels so I can see it a little bit more clearly. And now I'm going to go in and specify roughly one of my smallest diameters in here. So we're looking at about 1.5 microns. So this is what I'm going to use for my background subtraction. We're going to go to the next step, and here is where I have the threshold of my surface. And if I want to adjust it in any way, I can, but it looks pretty good. One thing I didn't explain earlier for people making surfaces, the very first visualization you see of a surface is an automatic threshold, okay? So you'll notice that when you come in, it always does a pretty good job at setting what that threshold should be. So this little icon over here, when you first come into the surface threshold step, has an A on it. A stands for automatic threshold. The minute you change it, it turns into an M, meaning it's a manual threshold. If you want to go back to the automated threshold, click on that button and it will switch it back to the automatic threshold. Okay? The reason I'm telling you that is for those people who have pretty big variations, so they want to compare different data sets, but some data sets are super bright and some are super dim. It's sometimes really difficult to find a value that will work well to threshold both of those images. So if you use the automatic threshold, we use the same algorithm every time to work out what that best fit would be. That would be what I would suggest for you guys. Also, some background subtraction ahead of time also helps as well. But I wanted just to point that out, that you have the option of using a manual or an automatic threshold. So once you've generated a surface, I'm just going to go through, and it looks like there's 5 different structures in here. I'm just going to go ahead and hit finish. So I now have a surface of this DNA, these chromosomes. So next thing I'm going to do is I'm going to create a 3D distance map. I'm going to make 2 of them. Now I'm hoping your iMacs are okay with this because I'm going to be adding new channels. And these iMacs are really not Imaris workstations. They're just for the purpose of tutorials. So when we add more channels, it puts more stress on the graphics card, which is pretty minimal on these systems. So I'm hoping you don't run into any problems. So what we're going to do is in this DNA object we just made, or the surface object, there is a little icon that looks like a pink gear. It's right at the end. So here are all the different icons, and right at the end is a pink gear. It's called our Tools tab, and inside of that there is a list of extensions. These extensions are MATLAB extensions, and they are written specifically to interface with Imaris. So they transfer some of our model information and statistics to MATLAB to do some calculations, and then MATLAB passes information back to us so we can do more. So in that list we have one called a distance transformation. So you're going to go ahead and click on it. Now this should launch MATLAB. So we've installed a runtime version on all of these systems, so it should work. And it should pop up with a little dialog box that asks you if you want to do, does it work?
Everybody might need to give it a second, just click it and wait. If you click it a million times, it'll keep showing up.
Okay.
Especially if you full screen, you might you go back to the original page, so unfull screen Imaris, and you'll probably have like a million versions of that letter. So you might need to click on
Has it actually opened up this dialog for anyone yet?
If you full screen Imaris, it won't. It's back in the original page.
So take it out of full screen. So there is a full screen option in the bottom right hand corner. I don't know if you've done it with Apple or whether you've done it here, but take it out of that. And what you should see is a dialog box that looks like what I have on the screen right now. Okay. I'm really sorry if it's not working. I just don't know. Oh, it is. Okay.
Yeah, it takes a second to show up if you're not.
Okay. So there is two ways we can make a distance map. We can use the boundary of the surface to determine distances inside of that structure, or we can use it to do outside of the structure. And it really depends on where the structures you're trying to measure are, if they're inside or outside. So I'm going to do one for both because I want to show you both ways. So I'm going to do one for the inside. It's going to run, and you'll see that it will create an additional channel, and depending on how you've labeled your surface, it will be called distance to something, DNA, whatever, blue, surface 1, whatever it is. Now this is an intensity channel, but instead of storing intensity values, it's storing distance information. So every single voxel has a unique distance from the closest boundary of that structure. So we're going to go into the slice view because I want you to see what this looks like. So make sure that your distance channel is turned on.
So, Lindsay,
Yeah.
so you know, none of these demo licenses are showing the name. So when you make the next one, you might want to make it a different color so people don't get confused because there's no words.
Names. Yeah, I don't know what's going on. I don't know. So apparently you have no labels on any of the channels and whatnot. I had no clue.
If you click on where the word should be in the panel, it tells you what the name is, but it doesn't show up in the display.
Awesome. Okay, so I will definitely show you how to change the color table. So for that new channel that you just made that has no name, we're going to click on the no name part, and that's going to open up a dialog that allows you to change the lookup table. There's an option in there called mapped color, and mapped color allows you to apply a custom lookup table. We're going to use one that's going to help us to visualize the changes in distance. So the one that I typically use is one called Fire, but you could use really whatever you want. So just something that shows changes in intensity with color. So if I click OK, we're hopefully going to see, first of all, that lookup table will be seen in your display panel or your display adjustment. And then if I grab the contrast tool for brightness, you're going to see that as I drag that down, you're going to see that inside the DNA, you have a heat map. Has everyone got something that looks kind of like this? Yep, okay. So the heat map is representing distance with color. So what I want you to do is if you put your cursor on any point inside of the nucleus or the chromosomes, you're going to see an intensity readout in the bottom left-hand corner. That intensity readout is showing you the intensity value for each channel in the image at the point where your cursor is located. So right now, I put mine right in the middle of a nucleus, and it's telling me 0.995. Okay? That's the distance in microns from the outer edge of that structure. Okay?
Did you set that up, sorry, with the measurement you've made? You need to do that first, do you? Oh, that's just there.
Separate, yeah.
Okay.
So this is basically what we refer to. So when you move your cursor around in the slice view, it's effectively like a voxel spy. You're basically putting your cursor on a particular pixel, and it's reading out the intensities in this bottom corner. So the intensity information for that last value is distance in microns from the closest edge of the surface, okay? Now, what we're going to do is I want you to add in the kinetochores. Okay, so you see for the most part, those kinetochores are sitting outside. I don't know enough about this to know if that's normal or not, but we're just going to go with it, okay? Okay, so those red spots are sitting outside the DNA. So we're actually going to do the distance transform thing again, but we're going to do one outside the DNA so we can measure proximity of those kinetochores to the DNA. So let's turn off that distance. Let's go back to the 3D view. Let's go back to that little pink gear icon and click on distance transformation again. Okay, now inside or in that dialog, you're now going to switch it to do one outside. And it's going to create another new channel, which will have no name for you guys. But we're going to, again, color code it so you can see distance. So I'm going to click on the name part, and I'm going to apply a different color table. I'm probably going to call it, I'll use the glow one instead. So it's kind of like a flame. And we'll go into the slice view, and I want you to turn off the original distance transform, the one for inside, and turn on the new one that we've made for outside. Okay, so it should look, I don't know if you use the same color table as me or not, but it should look something like this. Okay, now I want you to turn on the kinetochores. And I want you to see, actually this is going to be hard with this particular color table, but the kinetochores are occurring inside and outside. In this data set, I can see some inside and some outside. So we're going to use this distance map to actually calculate the distance, okay? But in order to extract that distance information from the kinetochores, we have to model them first. We got to create an object that detects them in the first place. So the first thing is, whatever your reference is, you make a surface, you make the distance transform, and then the next thing is you find the structure you want to measure. So we're going to go find the kinetochores. Now you can do this with surfaces, you can do this with spots. I'm going to do surfaces because I want to show you one other feature. So I'm going to do this as my, yeah, I can't even type that, so I'm going with kin. Okay, we're going to do the same thing again. This time it's with the red channel. Be very cautious when you start working with small structures with your surface default, with your surface detail default value. So when we were working with this data set, I think in the first session, these kinetochores are around about 0.5 micron or so. You've got to be careful with the surface detail for very small structures because you could be losing information, okay? So I'm going to go with background subtraction. I'm going to leave it at that 0.5 micron value, and I'm going to see what the default smoothing does. If necessary, I may need to come back and change it slightly. Okay, so I can already tell it's not quite right. So let me show you what I mean. So here's my kinetochores. If I use too much smoothing, they kind of get blurred and blobby. So it's hard to see them, they're not well defined. So I'm going to go back and I'm going to reduce my smoothing to about half that value. Okay, so I'm going to go with about, what, 0.65 or so? Sorry, 0.65. And I'm probably going to reduce my background value a little bit more to basically to increase the accuracy, really, of this segmentation. And that's going to give me something a little bit more along these lines here. So you should all be seeing something that looks like this. Okay? Now, there may be some of these that are touching one another. You can definitely use split touching objects if you want. For this, I'm probably going to do so because I can see a couple of them actually touching in Z. So I'm going to probably put in about 0.5 micron or so, which is going to put a seed in the center of each of these kinetochores. Now, a big thing I need to point out, if you use split touching objects and you don't have a seed in every single object, the objects without the seed point will not get detected. So you have to have a seed point in order for it to be detected. So if it's not got one, drag your quality filter down until it does. Also, to make it easier, I'll turn the DNA off. So it should look a little something like this. I'm using a quality filter of about 9. And then I'm going to the next step. And now I have each of my kinetochores, whenever the break occurred, you'll see that little crack in the surface. So we're almost there. So I'm going to go ahead and hit finish. So we have now a count. We now have all the volumetrics, all the morphologies, all the intensity information. But what I want to show you is we now also have distance, okay? Because we made a distance transform. So if you go into your statistics for the kinetochores and go to detailed, you're going to be looking for the distance information in the intensity channel that it belongs to. So right now we have 1, 2, 3, 4, 5, 6 channels. So we're going to be looking at the intensity in channel 6. And I'm going to be looking at minimum intensity. So the way this works is if you want edge-to-edge distance, you're going to use the minimum intensity. If you want center-to-edge distance, you're going to use intensity center. If you're going to want the max distance, so from the furthest edge to edge, you're going to use max distance. Intensity. So you're going to use min, center, or max. And you can also use a mean intensity if you want the average distance. Okay? So I'm going to use min because for most applications, people are looking for the minimum distance between one structure and another. So when I do that, it's going to pull up a list of measurements which gives you the distance in microns for every single structure. Okay? If a structure has a distance of 0, that means it's in contact with that reference structure. So if I turn on the nucleus here, this is actually touching the edge of the DNA. So it's a minimum distance of 0. Okay? Now, we've calculated distance. So the other thing we can do at this point is statistically color code. So if you go to the little color wheel, click on statistics coded, and in here go find your minimum intensity for channel 6. That will color code those kinetochores based on their distance in microns. So I have a lot of purple. The purple represents a 0 value. Anything that is not purple is not touching, and the color indicates how close or how far away they are from the closest DNA. Okay? Now that we have this distance information, now we can actually create subgroups. So we can go into this filter tool. It looks like a little funnel. We can add a filter in here. We can change that to min intensity for channel 6. And I'm basically going to find all of those that have a value of 0. Okay? And then going to hit duplicate selection to new surface, and this gives me now all of the structures that are in contact as a separate group. Okay? Does that make sense? Yep. Okay. Now, we just did this for the distance transform on the outside of the structure. You can also do that on the inside if you're looking to see where within the structure these objects are. So all of that information is stored in channel 5. So you can do exactly the same type of analysis with these kinetochores, but instead of just getting them all having a 0 value when they're associated with the DNA, if you use the inside value, you'll be able to see where they are. If they're completely like in the center of them or along the edge, you'll be able to get a little bit more information. So that would be in the intensity value, and in this case I may even use the center value. Intensity, ooh, it's not in my list. Okay. I'm going to show you real quick. Some of the statistics that we calculate are not automatically turned on. So there are statistics that we calculate that you have to go turn on if you want to see them. And you can access that by clicking on the really small tool icon in the bottom left-hand corner of your statistics table. It opens up your statistics configuration. You can go into your surface object, and here is a list of all of the statistics. You can turn on and off whichever ones are important to you. I would probably tell you, if you're using the BIDC and it's a shared facility, you probably don't want to turn a bunch of statistics off. You probably want to just add more rather than take them off, because it will potentially confuse some other people who are trying to get some numbers. So in here, I'm just turning on my center intensity value because it was previously turned off. And I'm going to click OK. Okay, so now if I look at intensity center for channel 5, these are all of my statistics. I'm going to change the statistics color coding to represent that same statistic so we can visualize it. And yeah, okay, so I'm looking at intensity center for channel 5. Anything that has a 0 value will be around the edge of the structure. And then depending on how close to the center that structure is, it will have a different value based on where it is within that structure. So you have options based on what it is you're trying to decipher from the data. Does that make sense? Yeah? Okay. Okay, so oops, PDFs, okay. So I'm going to now jump, because I want to try and give some time for some specific questions. I'm now going to jump to look at the cell model, which incidentally does a lot of these distance measurements for you as part of its creation. But we're going to look at a few different things with the cell model. So the object we're going to look at, or the image that we're going to look at, is the one labeled human embryo. Actually, it's not, but it is. It's called cell development, but it's actually a human embryo. Okay. I didn't collect it. It came from a group in France, but it's a pretty cool data set. So for right now, we're going to uncheck the cell object, because I want you to take a look at the data, because there's a couple of things that I want to work on. So the first thing, go away. There we go. So the first thing about this data set is, first of all, it's a membrane label for the cell, and it has a nuclear marker. It's also a time series. And if you play it, you'll notice that it actually rotates, it spins. Okay, so we've got a lot of things working against us here. Membrane label, dividing, spinning, a lot of things going on. So we're going to work on a couple of different things. I want to show you some new tools that are available to help you with some of these issues. So first thing, before we even go into the cell model, I'm going to turn the membrane channel off and look at the nuclear marker in here. And there's quite a bit of kind of background. It looks like there's little vesicles, little things inside of there, but I'm going to focus on the nuclei. And what I'm going to do is I'm going to use a surface, first of all, to find all of those nuclei. So I'm going to create a surface. I'm going to use absolute intensity because for the most part they all look very similar. So I'm going to use absolute intensity. I'm going to back off that threshold. And I'm going to just confirm that I'm seeing these nuclei in all of the time points. So I'm going through each of the time points, just making sure that I have a nuclei detected in each. Okay. Now there are some little structures getting picked up. This is where your classification part of your surface creation is really important. So I'm going to split touching objects in case those nuclei come close together. And I'm probably going to use a value around about 10 to 12 microns. I'll go back to the 3D view. So remember, the reason I'm using the split touching objects is to make sure that I'm getting them each as individual structures. So this, I got to this part just to show you using enable split touching objects. So make sure you have that activated and I've got that set to 12 at this point. Okay, so again, I'm just going to go through some of these time points and confirm that I have a spot in each one of the nuclei. Okay, and I'm going to go to the next step. Okay. Now, at this point, this is where I could classify filters, but one of the nice things about split touching objects is if it doesn't have a seed point in it, it gets removed. So if you had smaller pieces that you don't want to track, as long as they don't have a seed point in them, it won't get seen in the first place. So there may be no need to do further classification after a split touching object. So again, I'm just going to verify that it all looks as it should. And we're going to go to the next step, which is tracking. I'm going to skip over the edit surfaces. We'll go to tracking. Now, these cells are dividing. So I'm not going to use Brownian motion. I'm not going to use autoregressive motion. I'm going to use the lineage tracking algorithm. Okay. So in here, there is an option for algorithm, and we're going to use the very last one. Lineage is our cell division tracking. And I'm going to enter in a couple of pieces of information. So these cells are rotating, and so I need to be able to calculate how far they could actually move with that rotation, because I'm going to be tracking them. The purpose of the tracking is then I'm going to correct for the rotation using the tracks. So in this case, I'm going to just quickly measure from one time point to the next how far a cell could move. And it looks like, depending on the time point, that could be more or less. So I'm going to go from one time point here to another. Okay, and move up a little bit. There we go. This little hatched line, incidentally, we didn't look at it yet because we've done a lot of just straight lines in one z-plane. We also measure thickness. So you can put a point in one plane and then move up to slices on the side and put a point on another plane, and that hatched line that you can see is letting you know that it's measuring a distance in z. So I've just measured a distance of about 32 microns, 31.7 microns. So the value that is in the default max distance is actually going to work pretty well for me in this one. Gap size I'll leave at 2. That's the number of time points if a cell is undetected. For the most part, it looks like everything is detected, so in theory I don't need it, but I'll leave it in there just in case. And I'm going to go now to the next step. So we basically have a number of tracks that represent the movement of each of the nuclei as well as the division of each of the nuclei. And I'm going to go ahead and hit finish and go into that track editor. So do you remember we looked at the track editor a little bit ago and we were looking at these little straight lines? It becomes a lot more useful of a tool when you're actually looking at divisions, because it actually shows you where those divisions would actually occur. So what I'm going to do is I'm going to use the tracking information to help me to fix that rotation that I see in the embryo. I will be honest with you, I haven't tried this yet, so we'll see if it works. Okay, so what we're going to do is we're going to go in and select each of the tracks. Now I do have a shortcut for you with this. This is a new tool in 9.2. If you go into the Edit tab for the surfaces you just created, at the top there's an option called Selection for Pointer, Circle, or Box. This is a really tiny tool, but it's super useful. It means that instead of having to go in and select multiple options, if you go into select mode, you can make a little sphere or circle and select all of the objects within that region. So it's a multi-selection tool. But ultimately now I've selected everything at one time and all the way through the experiment. Okay. I'm going to go back to that track editor view and I'm going to go to correct drift. Now there is an option in there called reference frame correction. So something I kind of touched on a little bit this morning in my talk, but really didn't show in any other session today, was reference frames. But they are incredibly useful for helping you to correct for movement that's external to whatever you're trying to track. So in this case, I'm going to leave the default one selected, which is a reference frame correction. And I'm going to leave translational and rotational drift correction selected. And I'm going to click OK. And what that does is it puts a reference frame right in the center of all of those nuclei. And it also has put little, I'm going to point them out here, little markers on each of your time points, little green markers and magenta markers. Is everyone following, or is this?
Can you just go over that last step again?
Yes. Yes. Sure. Okay. So the last step with selection. So yeah. Okay. So what I did is I went into the Edit tab, and we have a new tool that allows you to select multiple objects at one time. So instead of having to go in and hold the control key down and click, 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 now if you change from pointer selection into circle or box, when you're in the select mode, you'll see this little box, circle. If you can change the size of that selection area with your mouse wheel, your scroll wheel, if you fit that around all the objects you're trying to select, it will select everything that is inside of that box. Okay? So the reason I'm selecting them is I want to use all of those tracks to help me normalize for that rotation that we have. Okay? If I selected just one of them, it may not be representative of what is happening with the entire embryo. So I select all of them, I go back into the Track Editor tab, and I go to the Correct Drift option. And that's where I can choose from a couple of different options. There are a couple of options in here. I'm choosing to show you the reference frame one. The other options, incidentally, would correct the image data. If something is rotating, that's probably something you don't want to do because you're going to lose resolution in order to try and correct the image data so that it is correct throughout the whole time series. Because if it's rotating, it's going through multiple different dimensions. And so if you try and correct for it, the chances are, especially with Z, you're going to lose some of your resolution as you correct your data. So a reference frames gives you another option to correct your data. So I'll show you exactly what it does. So has everyone got to the point? For everyone that wants to follow along, has everyone got to the point of having a reference frame? Yes? Adam is the only one that gave me a thumbs up. Ah. Okay, so, so we have this little reference frame in the center of my embryo. And this reference frame basically is showing me X, Y, and Z. Okay? And as I move to different time points, you'll see that that reference frame will rotate along with my embryo. Okay? So if I hit the play button right now, you'll see that my reference frame is rotating along with the embryo. Okay? Here's the beautiful part of a reference frame. If I just pause it for a moment, there is another tiny icon right in the corner, the left-hand corner. It looks just like the reference frame. If you turn that on and then hit the play button, you're going to see the reference frame will stay stationary and the image is now rotating around that. So turn the frame off and now you can turn the green channel back on. And what you have done is stopped the rotation of the embryo. Does that make sense? Yeah? I took the frame off because the frame rotating is really confusing. If you take the frame off and just look at the data, now you're like, oh, my embryo, at least you should be saying, oh, my embryo is not moving. But that's the purpose of a reference frame is instead of having to correct the data, you can set a point at which it will correct that movement, And the beauty of this is, now that we have that reference frame in there, now we can track the actual objects in without having that additional rotation in there. Okay, so it's corrected for the rotation. So this is just one example, but this can be used in lots of different examples. It doesn't have to be something that's rotating. It could be something that's drifting. It could be something that is vibrating, and so it bounces all over the place. But drift correction can be performed with a reference frame, and it can be a really useful tool. Okay, so I wanted to show you reference frame. So that was one example. I'm going to pause this. Reference frame can also be used to measure distances. So I place that automatically based on a central location of all of those surfaces that I created. You can also calculate distances using a manually placed reference frame. So I'm going to keep this one easy. If I click on the reference frame icon, which is in the top list of icons, it looks just like a reference frame. So if you click on that and add it into your list, you'll see that it's going to drop a reference frame in the origin of your image axis. So in your 0, 0, 0. So it drops it right in the corner. If you wanted to measure based on a particular point of interest that was not your image axis, you can, when you're in select mode, grab your reference frame and put it wherever you want. Okay? So maybe there's a particular plane that is of interest to you. It could be right in the center of the embryo, it could be the edge of the embryo, it could be the top of something, the bottom of something, the side of something. But you now have this new reference point, okay? A new 0 point that is separate from the image axis. Now I just moved this translationally. Did I say that word right? Translation, yes, I did. Okay, you can also rotate it. So if you're looking at something that's off axis, instead of it having it be in alignment with your image axis, you can also rotate. And you can do that by, when you're in select mode, grabbing one of your axes and rotating it in a particular direction. Okay? Now something that can be helpful with this reference frame is being able to visualize it, see it. So if I click on this little over here, this is the configuration for it, you can click to visualize particular planes. Sorry, I should look at my screen, not the projector. There we go. So this is my reference frame origin. Oops. This is my reference frame, and it's allowing me to see where I am placing that reference frame by using by showing these different planes of reference. Okay. Now, as far as distance is concerned, I'm going to move it slightly. And I'm probably going to dump it over here as an example. So I've already created some surfaces. I'm going to turn off the membrane label so I can see the surfaces, but now I'm going to go into the surfaces measurements. So I'm going to go to the statistics for the surface, and I'm going to find my distance from origin reference frame. Okay, so you have a distance from the image origin, which is all the way down in the bottom left-hand corner, and now I have another origin, which is the reference frame. So if I click on that, sorry, I moved a little, distance from origin reference frame, this value in here is a distance in microns for each of those surfaces to that reference frame. Okay? So if you are looking at samples where you have a wound or an injury, you can place a reference frame on that structure and be able to measure distance of other structures in reference to that point over time.
That would be time specific also, correct?
That would be time, but it doesn't have to be time. So we just did a distance transform where we used another structure as a reference point. We made the DNA our reference point and created a distance map from that. A reference point allows you to place a new origin. So it's an alternative. If you have a point of interest or a plane of interest, it's an alternative to using a distance transformation. Okay? Okay, so I just wanted to show you, so we have this different value in here for each of those surfaces. So just like we did previously, I can go in and statistically color code those surfaces, and I can do it based on the distance from origin reference frame. So I can color code to see how far those structures are from that origin. But you'll also notice all of my other tracking statistics in here have a reference frame option, meaning that they can be calculated based on a different origin than the image axis. Okay? I know it's the end of the day and it's a lot of information, but it's a pretty cool tool. It's I just wanted to show you it because it tends to be one of those things that nobody would find on their own, and it can be really helpful for specific analysis. Okay, so we're going to go back a step and we're going to look at the membrane aspect of this embryo now. Okay, so I did some drift correction for the rotation. I now want to show you some membrane detection. So if you have a membrane label, how can you automatically identify the cells and be able to measure and track those cells using a membrane label? So I'm going to turn the surface off, and I'll turn the reference frame off too, and I'll put the membrane back on, and I'm going to turn the nucleus off. One really cool feature about our membrane detection is we used to require a nuclear marker to help us identify the center of the cell. So what we would do is we'd find the nucleus, that would be the center, and then we'd fill the cell until we hit membrane. But in a live cell situation, nobody wants to mark the nucleus. They just want to mark the cell boundary, and they don't want to have to deal with lots of different labels or markers. So we now do membrane detection with or without a nucleus. Okay? So in this case, I'm going to show you without. So this image of the human embryo has a membrane all the way through the embryo, and I want to automatically find each of the cells so we can get morphology and then also track them through time. So let's go into the 3D view. We're going to create this time a cell object, so it looks like a little cell. Okay? It has a creation wizard just like surfaces, just like spots. It's the same concept, but we ask different questions because it's a slightly different tool. So the first thing we want to know is, what do you want to detect? So we have an option for the cell plus vesicles plus nuclei, or whatever they kind of look like. We have the cell plus nuclei, we have cell plus vesicles, and then we have just the cell. And we are going to use just the cell. Okay, because remember, this is the only tool that will do a membrane detection. So if all you want to do is find cells with a membrane, you're going to use the cell model and just use the cell only. Now that we've done that, we're going to, and I'm probably going to segment only because I don't want to be here even later today. So I'm going to just do a couple of time points so we're not here forever. So I'm going to segment a region of interest. And here is where I'm going to do this whole region, but I'm going to only maybe do about 5 time points. So the region of interest tool can be used for X, Y, Z, and also for time. So I'm going to do the first 5 time points. Okay. Now we're going to go to the next step, and this is where we can detect how the cell boundary is labeled. So we have one option for a cytoplasmic marker, and then we have one for a membrane. So if you click on the membrane, it's going to come up with a few parameters that we need to specify. So the first one is the channel that has the membrane label. So I'm going to change it to the green. The second is the smallest cell diameter. If you don't know what that is, use your slice view. So find one of your smaller cells. They're all about the same size, really. So this is, I'm measuring at about 46 microns, roughly. And remember, go up and down in Z. You don't want to be measuring the top of the cell. You want to get right in the middle of it. So go up and down in Z and find that midpoint. Also, if it's helpful, you can switch from slice into section view, which lets you see all 3 axes. And the reason this can be a little bit more helpful is there's a little extended view option which lets you basically fit a range bar around a particular cell. So I'm going to do it in X and Y, and then you can also do it crap. I moved the whole thing. You can also do it in Z. Okay, so this just gives you a way to measure all three. And it's measuring a little bit bigger than I'd measured myself, but I'm going to go with about 45 microns. So back to 3D, I'm going to type in my 45 microns. I'm also going to type in the thickness of the membrane. So that was the other measurement that I should have made when I was in there. So how thick is this membrane? So I'm going to say maybe a little bit less than that. I'm going to say about 2.5 microns. 2 microns is fine. That's the default value in there, so let's go with that. And then I'm going to leave it as local contrast, which is background subtraction. That's that more accurate segmentation. I'm going to go now to the next step, and I will tell you that it is taking the information you gave it and it's automatically segmenting for you. Okay, you're still going to get a little bit of tweakable, you'll still get some histograms to tweak, but for the most part, you've given it the information it needs to automatically segment this for you. So I have to be honest with you, I should have made you do one time point with your iMac. I don't know if you guys are having a problem or not, but it might take a while. Your iMacs are pretty low spec, so I'm not sure if is it working? What? Did it beat me? Better not have beat me. Okay. So what I want to show you is the first view that you're going to see is a slice through. So membrane detection is a tough one because you want to be able to see that it segmented it correctly, and if you just see it, in a 3D volume, you're not going to see that so easily. So we use something called a slicer display. So what you're looking at is the 3D volume, and then these little white lines are representing the boundary or where the membrane is. Okay? If you want to move that to see how well it has segmented throughout that whole structure, you're going to switch into select mode, click on the slice, and move it up and down. Okay? And that will let you see the boundary or that segmentation for all of the cells in there. Now, it does look like there's a little oh no, it's not, never mind. I thought there was a little something it was picking up, but it actually did a really good job. So we do have two little places where we can tweak how well this membrane detection has done. So intensity, if it's not picking up some cells, if they do not have any little white line around them, it could be that that intensity is really low, so you can drop the intensity value to help it look for a lower intensity membrane. Okay? Second thing, the quality filter is how well it is actually breaking up the cells into individual cells. If you look at a cell and it's broken up into many parts, you're going to back off the quality and you'll see that it will fuse them together. If you bring it too low, you're going to see it start breaking it up. And you can try it with this right now. So my quality value is 0.98. I don't know if it was around the same for you guys, but you can try by taking a look at the quality filter. For the most part, this is great data, so it doesn't actually do much. But if you can imagine lots of cells, lots of noise, there is potentially a need for you to adjust that quality. Okay, so the other thing we may want to do is check the other time points. Ooh, we have a missing cell in one of the time points. Yay. If you have a missing cell, it could be that that intensity was not low enough to pick up a dimmer membrane. So I dropped the intensity and it picked up that other cell. Okay? So check all of your time points to make sure that you have found all of the cells in all of the time points. Okay? So, next step. One of the things that our membrane detection does is it actually breaks your volume, your cube of data, into different parts. So even though we can see this little white outline where the cells are, that background itself is considered an object. Okay, it's a big object, one continuous object all the way around the cells. So typically you want to get rid of this object in the background, this background object. So I usually remove that top little peak, which is the background. You can leave it on because we can take it off later, but typically this is something, if you have something in the center like this with a bunch of background, it will have the background treated as if it is an object. So if you want to remove background, you're just going to get rid of that top end of the size bracket. And again, you want to check out the other time points to make sure that it's got rid of it for all of them. And then we're going to go to next. Okay, tracking. I'm really giving you some hard stuff right now. So the tracking stuff, I talked a little bit earlier about tracking, and I said there's 5 algorithms, except for cell, there's one more. So we have a tracking algorithm in cell that's not available in regular track, and it's called maximum overlapping, okay? And it's how we track a membrane detection, okay? Because a membrane detection is a little different. It's not like a nuclear division where it gets brighter and then one object pops into 2. A membrane kind of has this little divide that appears in between. So we have to use a slightly different algorithm in order to track that. So what we actually do is we compare the image before with the next image, and if there's 2 in the space, there used to be 1, and they're overlapping with the original one, we class that as a track. Okay? So we're going to use maximum overlapping. Okay. We also have a reference frame option in here just to make it more complicated. So we could actually incorporate the reference frame that we created to normalize for the rotation. That will help a lot because maximum overlap may not work very well if the cell in one time point is over here and then rotates around and is over here and divides. We won't see it. So it's probably a good idea to incorporate the reference frame that you may or may not have followed along with. So I'm just showing you as an example. And then also the maximum overlapping ratio is how much of the original cell has to be overlapping with the new cell. So 0.5 would be 50%. So 50% of the new cells are overlapping with the original cell. Again, I have no idea what it is for this particular cell, so I'm going to wing it a little bit. Okay. Oh, it looks pretty pretty. I don't know if you have it. I have a little spiral, but okay. I have something, at least. So what I want to show you is if you finish your creation, you're going to have a 3D reconstruction of that membrane detection. So let's turn off the volume, and you're going to see your embryo. Yay! And so the color coding is just to represent a different structure. So they're not statistically coded. It's just an object ID. It's just to let you know that's a different object than the neighboring object than the neighboring object. Okay, so we just color code them so you see that they're separate, divided structures. And in the cell model, you can go into that very first tab and you can change back into the slicer display. And that will show you each of your time points in that slicer display if you prefer. But when you finish creating it, you typically want to see it in a 3D model. Okay? I actually don't think my tracks worked very well, so I thought they did, but they don't look so good. I'm going to look at the track editor just to see if there was any division. Oh, I only tracked 5 times. There was no division. I tracked it for no reason. Okay. There was no division, so there was no real exciting information that was happening there, unfortunately. Anyway, so it did track, and it tracked the individual cells. So if you move from one frame to the next, you'll see that it tracked it. And hopefully this was the case for all of them. Anyway, so just wanted to show you. And also remember, if you want to fix it, meaning if you want it to stop moving while you play through, turn on the little reference frame. So click on your reference frame object, turn on the reference frame button in the bottom, and then you can move through and it should stay stationary. Is this too much, you guys? I'm sorry, it's a lot. Okay, so I just want to show you last for the cell model. I wanted to show you membrane detection because it's really cool, and there's a lot of people that use membrane labels, so this is now a solution for you to get that information out. But what I want to show you in the statistics is we give you the statistics on a cell-by-cell basis, and just like you saw with surfaces and all the other things, you can get information on the volume and the surface area and all of that good stuff. The other thing you can do is if you are measuring, if you have a nuclear compartment, you can actually measure intensity in the nucleus versus in the cytoplasm. So we remove nuclear intensity values when we calculate the size and the intensities of the cytoplasm. So we're trying to make Imaris a little bit more biologically aware, so now it actually knows that cytoplasm is not nucleus and that they're separate parts. So you'll notice in the cell statistics, you'll find names that pertain to a cell. So cell cytoplasm area, cell nuclear area, vesicles, that kind of thing. Okay. Any questions before I jump into filament tracer? Everyone looks kind of scared, and there's a few people kind of look tired. So I'm sorry, you guys. I should have probably put the advanced session first, because it's a lot more to process. So, okay. So we're going to jump from pretty human embryo to boring pyramidal cell. So there is a data set labeled pyramidal cell. It is a neuron that we're going to use for the purpose of tracing. Maybe I should ask, is anyone in the room interested in tracing? 1, 2, 3. Okay, we have enough. That's enough. So, and everyone else is just going to have to endure. So we're going to jump into some filament tracing. Now, I'm going to focus on neuron tracing, or what we call autopath, which is the tree-like branching structures, because that of the both of the algorithms is a little bit more complex. So I'll focus on that one, and then depending on our time, I'll maybe jump into the skeletonized too. So filament tracing is the last of our models. It is designed to give you length branching information, diameter information, and depending on what you're looking at, spine information also. So we're going to work with this pyramidal cell here. So you'll see it's an individual neuron. It has little dendritic spines the whole way along the processes, and we're only actually looking at part of the cell. Okay. Incidentally, this is a great example to use with the new blend peak mode. So I talked about it this morning a little bit, but our blend mode makes the structure look more solid and more three-dimensional. And when it comes to neurons, they are so complex that sometimes using the blend technique really helps you to visualize the branching patterns and things like that. This is the same for blood vessels too. So if you turn on the blend mode and go into the graph shape peak, and then bring these two peaks together, or these 2 points together. There we go. Got it. Okay, bring these 2 points together. Bring your opacity down a little bit. You're going to get an image that looks like this. Okay? Now, the reason I'm pointing this out is when we start building our filament model, this visualization is going to make it a little bit easier for us to do it. Okay? So I'm going to keep it in this peak mode. For those of you who don't want to go there and just want to, keep it easy, don't worry about this. It'll work either way. This is just visualization. But what we're going to do right now is we're going to add in a filament object, which looks like a little leaf icon right next to the cell one, this one right here. So if you click on it, it will add a filament object into your list, your object list. And that filament object, like every other model, has a creation wizard with parameters that we need. So the first thing that we need to specify is the algorithm we're going to use. So for neuroscience, for people with cell bodies with projections coming out of it, you're going to use the default algorithm, which is called autopath. For those of you who are going to be doing this with blood vessels or microtubules or just long, thin things, you're going to be using the second option, which is called threshold. For right now, it's a neuron. I'm going to use autopath. Okay, I'm going to go to the next step. Next step is the channel you want to use to make the model. So this is a single channel image, so that's easy. But it asks me for two pieces of information. It asks me what the start point diameter is, the largest diameter, as well as the thinnest diameter, which is the thinnest projection you're trying to trace. So we're going back to our trusty slice view. And this is going to be useful for identifying how big the start point is, which is down here at the bottom. And it's about 6 microns. I'm then going to go in and measure the projections, and that's measuring, I'm probably going to use about a micron, but it's measuring just under a micron. Okay. So 6 microns. Oh, actually, that's actually the default values is what I measured, so I'll probably leave that. You know what, I'll put it as 1, just to make it simple. Okay, so I'm going to now go to the next step, and what we're going to see, and the reason why this peak mode is so useful, is you'll see that the projection is being represented by spots. Okay, we have 2 different colors. We have a cyan color, which is the start position, and then we have white ones, which are we refer to them as seed points, but they are the projections themselves. Okay, so ideally what you want to see is seed points, white seed points throughout all of the projections, and then only a cyan sphere in a start point. If you have a bunch of start points all over the place, that's an indication that you probably set that size too small, and it's looking for lots of different things. So if it really is representative of a cell body, you shouldn't have too many of them. Okay,
So if you have multiple individual cells in your field of view, so will it calculate?
Absolutely.
Okay.
Absolutely. You just need to make sure that every cell has a start position inside of it. If you forget one, it will think that projections from another cell belong to the neighboring cell. So you really need to make sure you have a start position in every single cell body. Now there are going to be situations where cell bodies may be right on the edge of the image, maybe a little bit dim for some reason, so you can manually intervene and place your own start positions as well as your own seed points. So to do that, if you go into select mode, you're going to see a little box at the end of your cursor. If you place it in a specific location, hold down the Shift key on the keyboard and right click. Right click will place another start position. Left click will place a seed position. So 2 different types. You're either trying to help it with a projection or you're trying to identify a start position. Also, if you have seed points that you want to remove, you do the same thing, Shift click on the ones you want to remove. So Shift right click. Oh God, I had this the last time. There we go. Shift right click to remove a start point, Shift left click to remove a seed point. Okay. I think there's a shortcut somewhere that they put, but I can never find it. They keep telling me they put it somewhere and I don't know where it is. Anyway, Shift right click, Shift left click, depending on those 2 different spheres. You also have a threshold that you can use to specify whether it's actually finding your dim structures or not, so you can incorporate that. Okay, so we're now going to go to the next step, and this is where I don't know if your iMacs are going to be happy with you right now or not, but what you should see is something that looks a little bit like this. So it looks like a surface model on top of your neuron. If you peel this threshold back, you will see a white trace line through the center of your neuron. Are we good? Do we see something like that? Okay, so this step actually does 2 different things. It's letting you visualize what's been traced with that white line. It also allows you to calculate the diameter of those projections by using a surface. So the surface is basically there to define where the boundary of the projection is. At every single vertice along the trace, we will calculate the diameter or the distance between that point and the closest surface, and that's where we get the diameter information from. Okay. Okay, I'm going to go now. I'm sorry, the algorithm. This is the advanced group, so I'm going to describe this. Shortest distance from distance map. At every single vertices along your trace, we look at that point to the closest surface that we hit, and we make a little circle that resembles that distance all the way around that vertices. Okay, so basically a filament is a series of circles that are connected together to make a tube. Okay. The second option, called approximate circle of cross-section area, gives you a little bit more of a specific diameter calculation, because instead of just measuring from that little vertices to the closest surface and making a circle, it actually does a cross-sectional area and creates a circle that is equivalent to that cross-sectional area. So if you have boutons, or if you have, did I say that right? I love that word. If you have little kind of varicosities along your projection, the second technique will help you to see those better, whereas the first technique kind of averages out a little bit. Okay? So depending on what it is you're looking for, you can choose a particular algorithm, and then whatever algorithm you use, just use that consistently for all of your analysis. Okay. So I'm going to go with the default. In fact, I might show you both. So this is the shortest distance from distance map, the default. It kind of looks like just a tube. If you go back a step and try the other option, you'll probably notice that it'll get thinner and thicker and thinner and thicker, and you'll see these kind of undulations along the projection. So some people that are looking at dendrites don't really want to see that. They think that's almost like an artifact, and that's not what it should look like. So I would say the majority of people use the first and the default option for diameter calculation. For those of you who are looking at dendritic spines, you have to choose one of them and use it consistently, because it will impact your spine calculations if you change it from sample to sample. Okay? Detect spines. Is anyone looking at dendritic spines? We're not going to do this right now, so just forget it. And we're going to hit the finish button. Now your dendrites are probably going to look different depending on what algorithm you used for diameter calculation. I went with the second option, so mine is a little bit more dramatic. Yours is, if you use the first option, is probably looks more like just regular tubes. So I'm going to turn the volume off so we can take a look at what we have here. But these are basically, this is the filament trace that we've created. You can visualize the trace in a line profile, as a cylinder, or in the cone view, which brings in your diameter information. Okay, so however you want to visualize. A lot of people that are just interested in length and branching just want a line. They just want to see the line profile. And also, that works particularly well when you are verifying how well it has traced your neurons, is if you have the line in with your peak mode, so you can see it running through the middle of it. Okay. Couple things I'm going to show you. Statistics color coding also applies to filaments. So if you want to color code by a branching hierarchy, you can go in and change the statistics color coding to look at your branching. And if I turn my volume off, you can hopefully see that I have different colors representing primary dendrites versus secondary versus tertiary. And then we also have a different branching hierarchy calculation that basically every time a branch is formed, those resultant projections become the next level. So it depends on how you want to calculate it, but we can visualize that. We can also get all of the statistics from this filament object, and I will tell you there is a lot. Okay. So depending on what it is you're looking to measure, I'm going to give you a little tip. If we click on this little configuration button in the bottom corner of your statistics, it's going to take you to your statistics configuration. If you right-click on any of those statistics and click on Show Help, it will bring you to our reference manual. There's a very useful part of our reference manual. Our reference manual is very long. I don't recommend anyone read it. It is huge, and it's actually not very helpful apart from this part. This is the description of how all of our statistics for every model are calculated. So for a lot of people who are publishing using Imaris, and they want to, and they've used Imaris to calculate specific statistics, you may actually want to know what formula was used or how that was calculated, and this will describe it all for you. So if we go into the filament model, it actually gives you a breakdown of the naming convention and what that pertains to. And as you scroll down, we give you a description and an illustration of every single statistic. This is the same for spots, cells, and surfaces. Okay? So the reason this is so important for filament is because some of the measurements may not make sense to you. So you may not know what shoal intersections are. You may not know what how dendrite straightness is calculated. So all of the, and how a branching angle is calculated, but it's all described in there for you. Okay? Okay. I should ask at this point, is there any questions for the people that raised their hands and said they were interested in filament? Was there any questions that you guys had regarding this?
Just that this could be applied for like a larger organ that would branch similarly, right?
Absolutely. So because we're all running on these smaller systems, I'm using demo data, which is small. Typically people are using the filament model on whole brains or much bigger sections. Now, one thing I will tell you is they're not using the automated creation to do it. And the reason for it is if you have this huge organ or tissue, you may not want to actually deal with all of it. You may actually only want to look at a couple of neurons and see where they go. So one of the things that we do or that we've done recently is optimize our auto tracing algorithms, semi-automatic tracing algorithms. And they're actually sometimes faster than the automated. So let me show you how this works. So I'm going to turn on my neuron. Yes, I need that, sorry. Let me just turn off my peak for right now. I'm going to just put it back to looking somewhat normal. I may even put it back to maximum intensity projection. Okay, I created a new filament, and the very first step, there's a button that says skip automatic creation. So if you do that, it takes you straight to a filament tab. And the one it's taking you to looks like a paintbrush. It's called the draw tab, okay? The semi-automatic tools allow you to basically define your start position and then define where a neuron ends, and it will automatically trace between those 2 points for you. So this is how it works. So we're in AutoPath. You need to give it an idea of your diameter of your projections. Tell it what the channel is that you're going to be using. Over in the 3D view, make sure you're in select mode. Shift right click to mark your start position, and then as you move your cursor, you'll notice that it will trace automatically along those projections for you. Okay? It's called an AutoPath technique because it automatically finds the path between where you specified your start and where you specified your end. Now, if you hold the Shift key down and left click, that will mark that particular branch, and then you can continue, like so. Make sense? So it's really quick. It's been optimized to be really fast, but it's more typical when people are looking at big sections that there's particular neurons that they may have. Maybe it's transfected. It could be lots of different things. It could be injected, whatever it is. But this is usually the way that they would go about it. Rather than having everything considered as an option, they focus in on what it is they actually want to measure. And this tool, as I said, can actually generate your statistics faster than doing it automatically. Now, what I did want to show you is all the statistics are already calculated. So as you're tracing, it's automatically calculating all the branching, all of the information that you need for the purpose of tracing. Okay. How big is the data that you're potentially looking at?
It's not for multiple neurons in an organ. It would be for a branched epithelial organ.
Oh.
So like the lung
Oh.
or the pancreas or something like that.
Awesome. Okay. So typically for that kind of thing, I would use the other technique.
Okay.
So we have another technique called threshold. I don't think I'll have time to go over it. Okay, it's 6 o'clock and I promised you some time to answer questions.
I have an appointment with you tomorrow.
You do. Let's do it then.
Okay, okay.
Perfect. Okay. I actually have some lung data if you don't. Do you have something you want to trace?
Yeah, I actually, yeah, I think I could, yeah.
Cool. So, okay. I hope I was able to show you some stuff you didn't know previously. I hope I was able to answer some of your questions without you having to ask them. But if you have questions now, let me know. I think we have this room till 6:30, so I can be here for another half hour. But does anyone have a specific question that I have not addressed or a problem that you need an answer for? And you don't have a one-on-one session with me tomorrow. No. Everyone looks tired. So I hope that was helpful. I hope that this gives you a little bit of an idea of what you can do with your own data. Hopefully, I actually think there might be a session or two available tomorrow for anyone that does still want to sign up for one-on-one. But if you don't have any other questions, then I'm going to let you guys go.
Real quick, guys, because most, if not all of you guys are involved with VIUC, I'm going to be sending out a survey, and since you guys are the more advanced users, I'd really, really like to hear